Welcome to my 17th tutoring session in A-level chemistry. In this video, you will learn about the modern periodic table of the elements. I am presenting this topic in a three-part series. Part 3 video is continuation of previous two videos on the topic periodic table. Watch the previous two videos, as these two videos will provide a better understanding of the content in this video. Link to these two videos is given in the description. Please take a moment to watch these videos. Periodic table is a versatile tool to organize and understand the properties of elements. In the periodic table, you will find a total of 118 elements, of which 94 are naturally occurring on Earth, while the rest 24 are of synthetic origin. That is to say, they are synthesized in the laboratory using nuclear reactions. I have highlighted the synthetic elements in the periodic table. Elements from atomic numbers 104 to 118 and elements from atomic numbers 95 to 103 are of synthetic origin. So these elements can be synthesized using nuclear reactions. Elements are classified as metals, non-metals, and metalloids, depending on the properties they possess. I have color-coded the elements in the periodic table. Metals are highlighted in yellow, non-metals are highlighted in green, while the metalloids, they are highlighted in pink. So here are some properties of metals that are highlighted in yellow in the periodic table. Metals are electropositive in nature. That is, they lose electrons in reactions and form positive ions. For example, group 1 elements like sodium loses one electron to form electropositive ion with +1 charge. Group 2 element like magnesium loses 2 electrons in reactions to form positive ions with +2 charge. Group 3 elements like aluminium loses 3 electrons in reactions to form positive ion with +3 charge. Metals also form salts. Metals react with non-metals to form the salts. For example, sodium metal reacts with the non-metal, that is chlorine gas, to form sodium chloride. Metals form ionic bonds with non-metals. Now, ionic bonds are formed by transfer of valence electrons from one atom to another to form oppositely charged ions, like for example, sodium ion and chloride ion. These oppositely charged ions, that is Na plus and Cl minus, are held together by strong electrostatic force of attraction between them. And that also leads to the stability to the compound. Non-metals are highlighted in green in the periodic table. Here are some important properties of non-metals. Non-metals are electronegative in nature. That is to say, they gain electrons in reactions and form negative ions. For example, group 7 element like chlorine gains electron to form a negative ion with -1 charge. Group 6 element like oxygen gain 2 electrons to form negative ion with -2 charge. Group 5 element like nitrogen gains 3 electrons in reaction to form negative ion with -3 charge. Non-metals also form salts. Non-metals react with metals to form salts like sodium chloride. So when non-metal like chlorine, now chlorine, it does not exist in nature as an elemental form. It exists in the gaseous form. That is, chlorine exists as a diatomic molecule in nature. It reacts with sodium metal to form sodium chloride. One of the important property of non-metal is covalency. Now non-metals form covalent or molecular compounds with other non-metals via the covalent bond. Now in the covalent bond is formed by mutual sharing of electrons between the atoms involved in bond formation. For example, in case of hydrogen molecule, covalent bond is formed by mutual sharing of a pair of electrons between two hydrogen atoms involved in bond formation. While in case of oxygen molecule, two covalent bonds are formed between the two oxygen atoms involved in bond formation by mutual sharing of two pairs of electrons. Examples of other important molecular compounds involving covalent bonds are water molecule and carbon dioxide molecule. In the periodic table, metals and non-metals are separated by a third class of element called metalloids. Metalloids are highlighted in pink, and you can see the metalloids in the periodic table in the form of staircase, and the metalloids are arranged in the form of a zigzag line. Metalloids, they show properties of both metals and non-metals, and that is why they're also called as semiconductors. Now there are a total of 7 metalloids in the periodic table: boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. So these are the 7 metalloids in the periodic table that are highlighted in pink color. Now the elements from atomic numbers 57 to 71 and elements from atomic numbers 89 to 103 are called inner transition metals or inner transition elements, and you can find them below the periodic table in 2 rows. Elements in the top row are called lanthanides, while the elements in the bottom row are called actinides. Now both lanthanides and actinides, they are radioactive in nature. Now elements in the periodic table are organized in 18 columns called groups and 7 rows called periods. Period 1 elements have just one electron shell that are present in row 1. For example, row 1 elements are hydrogen and helium. Both hydrogen and helium have just one electron shell. Hydrogen has one electron in the shell, while helium has 2 electrons in the only shell. So period 1 elements in row 1 have 1 electron shell. Period 2 elements in row 2 have 2 electron shells. Period 3 elements in row 3 have 3 electron shells. Period 4 elements in row 4 have 4 electron shells. Period 5 elements in row 5 have 5 electron shells. Period 6 elements in row 6 have 6 electron shells. Period 7 elements in row 7 have 7 electron shells. Now elements in the periodic table are also organized in 18 columns called groups. As per the IUPAC system of nomenclature, these 18 columns called groups are numbered from 1 to 18. These 18 groups are also labeled by traditional numbering system using Roman numerals followed by capitalized letters A and B. 1A, 2A, 3B, 4B, 5B, 6B, 7B, 8, 9 and 10 will be 8B, 1B, 2B. Now capitalized letters A and B are used to label the group elements. Group A elements are called main group elements or representative elements, while the group B elements are called transition elements or transition metals. Group 1 elements have just one valence electron in their outermost valence shell. Group 2 elements have two valence electrons in the outermost valence shell. Group 3 elements have three valence electrons in their outermost valence shell. Group 4 have four valence electrons in their outermost valence shell. Group 5 have five valence electrons in their outermost valence shell. Group 6 have six valence electrons in their outermost valence shell. Group 7 have seven valence electrons in their outermost valence shell. And group 8 have 8 valence electrons in their outermost valence shell. Now group number is equal to the number of valence electrons. That is to say, group 1 elements have 1 valence electron, group 2 elements have 2 valence electrons, group 3 elements have 3 valence electrons, so on and so forth. Now group 1 elements with 1 valence electron in their outermost valence shell, they lose this only electron in reactions and form positive ions giving a +1 charge, and therefore it has an oxidation number of +1. Group 2 elements lose 2 valence electrons in reactions and form positive ions with +2 charge, giving them an oxidation number of +2. Group 3 elements lose 3 valence electrons in reactions and form electropositive ions with +3 charge. Group 5 elements lose, no, they don't lose. Now group 5 elements, they gain electrons. Group 5 elements, they gain 3 electrons in reactions and form negative ions with -3 charge, giving them an oxidation number of -3. Group 6 elements have 6 valence electrons in their outermost valence shell, and they gain 2 electrons in reactions and form negative ions with -2 charge, giving them an oxidation number of -2. Group 7 elements gain 1 electron in reactions and form negative ion with a -1 charge, giving them an oxidation number of -1. Now coming to the last and the interesting group, that is group 8. Now group 8 elements have a total of 8 valence electrons in their outermost shell. They have a stable electronic configuration with a full octet of electrons. They do not gain electron, they do not lose electron, nor they share electrons in reactions. That is to say, they do not participate in any reactions. They are chemically unreactive or chemically inert. And that is why, as a result, no charge is associated with this particular group of elements, giving them an oxidation number of 0. And that is one of the reasons why this group is also called as zero group elements. Now you may be wondering, why is that I have not mentioned the valence electrons in case of elements from group 3 to 12? That is because elements from group 3 to group 12, they have variable oxidation states. Now group 3 to group 12 elements, also called as transition metals, because of their multiple oxidation states, they form positive ions with different charges, with +1, +2 and +3 charge being the most common one. So because of their variable oxidation states, so it's very difficult to give the exact number of valence electrons in case of the transition metals because of their variable oxidation states. And that is why they are categorized as transition metals. And transition metals, they have set of d orbitals filling with electrons, and they also have a ability to act as catalyst. So in a nutshell, metal like sodium reacts with non-metal like fluorine gas to form an ionic compound, for example sodium chloride. Now for further updates or for the recent updates on the periodic table of elements, you can visit the homepage of International Union of Pure and Applied Chemistry. I have given the link in the description. Please follow that. Now elements in the periodic table, they are also categorized as S, P, D and F block elements. So the periodic table is divided into 4 blocks. You can find the S block elements towards the left side of the periodic table. You can find the P block elements towards the right side of the periodic table. And you can find the D block elements sandwiched between S block and P block elements. And what about the F block elements? You can find the F block elements right below the S, P and D block elements. Now groups 1 and 2 are S block elements. Groups 13 to 18 are P block elements. Groups 3 to 12, also called as transition metals, are D block elements, while the inner transition elements, lanthanides and actinides, are F block elements that are radioactive in nature. So depending on the types of orbital that is being filled with valence electrons, the elements are categorized as S, P, D and F block elements. So S block elements have their valence electrons in S orbitals. P block elements have their valence electrons in P orbitals. D block elements have their valence electrons in D orbitals, while F block elements have their valence electrons in F orbitals. Let's take a closer look at group 1 elements, also known as 1A. Group 1 elements are also referred to as alkali metals. Now group 1 elements, as I already mentioned, they have only one valence electron in their outermost shell. So group 1 elements lose this valence electron to form electropositive ion in reaction or during reaction with a +1 charge, giving them an oxidation state of or oxidation number of +1. Now, oxidation state and oxidation number. Now, these two are used interchangeably. The meaning is one and the same. Oxidation state and oxidation number meaning is the same. So, they are used interchangeably. So, oxidation number is +1 in case of group 1 elements. So, there are 6 alkali metals in group 1 of the periodic table. They are lithium, sodium, potassium, rubidium, cesium and francium. Now, group 1 elements, as I already mentioned, have one valence electron and they can easily lose this one valence electron to form positive ions, giving them an oxidation state of +1. For example, formation of sodium chloride. Now, during the formation of the table salt sodium chloride, sodium undergoes oxidation and loses one electron, which you can see in the reaction, while chlorine gains one electron and undergoes reduction, resulting in formation of chloride ion. So this is how sodium chloride is formed from sodium and chlorine gas. Now let's examine the electron structure of sodium to understand this. Now sodium, it has one valence electron in its outermost shell. During the oxidation reaction, it loses only valence electron. And forms a positive ion, that is sodium ion, with a +1 charge. So what is the driving force for the sodium, that is group 1 metal, to lose its valence electron? The reason is it loses its valence electron to achieve the stable electronic configuration. Also, to attain a stable electronic configuration, it loses its only valence electron. And neon gas is nearest to sodium in the periodic table. So sodium loses its only valence electron to attain the stable electronic configuration of neon, as neon is the only noble gas that is nearest to sodium in the periodic table. So now we know the reason why group 1 elements lose only one electron in a reaction. That is to attain the stable electronic configuration, similar to that of the noble gas that is nearest to them. So sodium has to lose one electron to attain the stable electronic configuration of neon. Reason being, neon is the noble gas nearest to them in the periodic table. And in this reaction, sodium undergoes oxidation and is oxidized. Now, why group 1 elements are called alkali metals? There should be some reason behind this. So they are called as metals because they easily lose electrons to form electropositive ions, that is cations, and therefore tends to form positive oxidation states. Now, why they are called as alkali metals? So they are called metals because they lose electrons to form electropositive ions. Fine. Why they are called alkali metals? Because group 1 elements and their oxides react with water to give strongly alkaline solutions. That is, strongly basic hydroxides are formed. So that is the reason why group 1 elements are called alkali metals. So sodium reacts with water to form sodium hydroxide. It is strongly basic in nature. And in this reaction, hydrogen gas is liberated. It's a highly exothermic reaction. So oxide of sodium, that is sodium oxide, again reacts with water to form strongly basic sodium hydroxide. Now let's take a closer look at group 2 elements, also known as group 2A. Group 2 elements are referred to as alkaline earth metals. Now group 2 elements have two valence electrons and they lose these two valence electrons in a reaction to form electropositive ion with a +2 charge, giving them an oxidation state of +2. So there are 6 alkaline earth metals in group 2 of the periodic table. They are beryllium, magnesium, calcium, strontium, barium and radium. Group 2 elements have 2 valence electrons and readily lose to form electropositive ions with +2 charge, giving them an oxidation state of +2. So for example, magnesium, it's a group 2 element. It's a solid, reacts with chlorine that exists as a diatomic molecule in nature. So magnesium reacts with chlorine to form magnesium chloride. Now let's examine the electronic structure of magnesium to understand why it loses its 2 valence electrons. So magnesium has 2 valence electrons in its outermost valence shell. It loses its 2 valence electrons in the reaction to form electropositive ion with +2 charge. So what is the driving force for the group 2 element magnesium to lose its 2 valence electrons? So driving forces to attain the stable electronic configuration similar to that of neon, because neon is the only noble gas nearest to magnesium in the periodic table. So why group 2 elements are called alkaline earth metals? Let's see why they're called metals. Group 2 elements easily lose electrons to form electropositive ions, that is cations, and therefore they're called as metals. And why they're called as alkaline earth metals? Now group 2 elements occur in the earth's crust as oxides, and they're not found in their elemental form. They exist in the salt form and are extracted from minerals. So this is the reason group 2 elements are called as earth metals. And why they're called as alkaline earth metals? Because of their chemical properties. So group 2 elements and their oxides are basic or alkaline in reaction with water. So they react in water to give strongly alkaline solution, basic hydroxides. So the term alkaline refers to the basic or alkaline nature of their oxides and hydroxides, which form strong base when dissolved in water. Moving on to the group 13 elements. So group 13 elements are also known as group 3A metals, elements. Group 13 elements are also referred to as boron group or trials. So they are called as trials because in Latin, trial means 3. They got 3 valence electrons. That is why group 13 elements are also called as trials. So group 13 elements have 3 valence electrons, their outermost valence shell. They lose these 3 valence electrons to form electropositive ion with +3 charge, giving them an oxidation state or oxidation number of +3. Group 3A elements have 3 valence electrons with an oxidation state of +3, as already mentioned. For example, group 3 element aluminium reacts with chlorine to form aluminium chloride. Now let's examine the electronic structure of aluminium to understand why exactly group 3 elements lose their 3 valence electrons in a reaction. So aluminium has 3 valence electrons in its outermost valence shell. It loses 3 valence electrons in the reaction to form electropositive ion with +3 charge. And what is the driving force for this? Now aluminium loses its 3 valence electrons in order to attain the stable electronic configuration of neon, because neon is the only noble gas with stable electronic configuration, which is nearest to aluminum in the periodic table. So neon gas is nearest to aluminum in the periodic table. That is why it tends to attain the stable electronic configuration of neon. Now coming to the most important block in the periodic table, that is D block elements. Now elements belonging to groups 3 to 12 are called the transition metals, also called as D block elements. And as per the IIIA system of nomenclature, the groups are numbered from 3 to 12. So transition metals comprise groups 3 to 12 of the periodic table. Now these elements, also called as transition metals, they are characterized by the presence of partially filled d orbitals in their electronic configuration. So here are some examples showing the presence of partially filled d orbitals in transition metals. In case of iron, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s2. So I highlighted the d orbital showing that it is partially filled. Now d orbital can accommodate a maximum of 10 electrons. So d orbital has 5 subshells and each subshell can accommodate up to 2 electrons, not more than 2. So d orbitals with 5 shells can accommodate up to a maximum of 10 electrons. So in case of iron, you can find only 6 electrons filled up in the d orbitals. So in case of cobalt, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d7, 4s2. So again, you can see the d orbital is partially filled. In case of manganese, again the d orbital is partially filled with only 5 electrons. So d orbitals can accommodate a maximum of 10 electrons. So transition metals are characterized by presence of partially filled d orbitals. So here are some key characteristics of transition metals. Most important property is that transition metals have multiple oxidation states. For example, copper, its normal oxidation states are +1 and +2. So here is a table showing the oxidation states of some transition metals: vanadium, chromium, manganese, iron, cobalt and copper. So you can see that the d orbitals are partially filled. Now to represent the oxidation states of these transition metals, now the oxidation state is represented by Roman numerals within the parenthesis following the name of the metal ion. So first you start with the name of the metal ion followed by the Roman numerals within the parenthesis representing their oxidation states. For example, iron, it has 2 oxidation states, the common oxidation states being +2 and +3. So how do you indicate? First you mention the name of the metal ion, that is iron. This will be followed by their respective oxidation states in Roman numerals within the parenthesis. So iron 2 for +2 state and iron 3 within parenthesis for +3 states. So similarly for copper, copper 1 and copper 2, and for chromium, which is having the oxidation states of +2, +3 and +6, will be mentioned as Roman numerals 2, 3 and 4 within the parenthesis following the name of the metal ion. Now this convention is to specify the charge on the metal ion, because as I already mentioned, the transition metals have multiple oxidation states, and this convention will be useful in mentioning the specific charge on the metal ion. Now, second characteristic is that transition metals form complexes. Now, what is the driving force for the transition metals to indulge themselves in forming complexes? Once again, the answer to this lies in the partially filled d orbitals. So, transition metals with partially filled d orbitals, they thrive for electrons. So, they make an attempt to fill this partially filled d orbitals by forming complex with electron rich species, that is Lewis base. So, I have given the example of a complex where copper is forming a complex with ammonia. So, here in this example, copper is the metal, ammonia is the ligand, copper is the acceptor of electrons, ammonia is the donor of lone pair of electrons, which is present on the nitrogen atom. Copper is electron deficient, ammonia is electron rich. Copper is the Lewis acid, ammonia is the Lewis base. So complex is formed between copper and ammonia by means of coordinate covalent bond. Now in a coordinate covalent bond, both the shared pair of electrons come from the same atom or the group. Here in this case, in case of ammonia, there is a lone pair of electron in the nitrogen atom and making ammonia as a electron rich species, making it as act as a Lewis base. And that is how a complex is formed between copper and ammonia by means of coordinate covalent bond. Now transition metals are also known for their catalytic action. Transition metals like nickel, platinum and palladium, they can be used in catalytic hydrogenation reactions. Some of the examples are vegetable ghee can be prepared from vegetable oils by catalytic hydrogenation reaction. That is a preparation of saturated glycerides. And even saturated aliphatic hydrocarbons can also be prepared from alkenes and arenes. Now coming to the most important property of transition metals, that is paramagnetism and ferromagnetism. So let me start with paramagnetism. As I already mentioned, transition metals are characterized by presence of partially filled d orbitals. So d orbital has 5 subshells and each subshell can accommodate up to 2 electrons. And d orbitals can, as a whole, d orbitals can accommodate up to 10 electrons. Now, paramagnetism is a property of transition metals with one or more unpaired electrons in the d orbitals. So, what is the requirement for a metal to show paramagnetism? There should be one or more unpaired electrons in the d orbitals. So what happens if there are unpaired electrons in the d orbitals? Let's see. Now, charges in motion always generate a magnetic field. So electron is a negatively charged particle, so it's no exception. So electron being a negatively charged particle, it has a property called spin. It spins on its own axis. So because of this spinning motion, it generates a magnetic field and making it paramagnetic. So paramagnetism is a property of substance with unpaired electron. So what if the orbital is having a paired electron? What if there is paired electrons? Let's see. So even if they're paired, the spinning property will be there. Each electron will spin on its own axis and generate its own magnetic field. Now because the spins are paired, the magnetic field created by the each electron will be mutually cancelled. So in case of paired electrons, spins are paired and therefore the magnetic fields will be mutually cancelled, making it diamagnetic. So this is the difference between paramagnetism and diamagnetism. So paramagnetism is a property exhibited by substance with the unpaired electron, while diamagnetism is a property exhibited by substance with paired electron. So you find unpaired electrons, or you can find d orbitals in transition metals with only one electron, and thereby making it paramagnetic. Now what is ferromagnetism? Now ferro is the Latin name for iron. So when you observe the electronic configuration of iron, you can find that there are 4 unpaired electrons, and as a result it generates a magnetic field, and these materials, they display magnetic properties. So ferromagnetic materials, they display magnetic properties under the influence of a magnetic field. That is when the magnetic fields or the magnetic lines align with them, making them magnetic in nature, displaying magnetic properties. So that is why iron, it gets attracted to the magnet. So these are some of the most important characteristics of transition metals. Now let's take a closer look at group 17, also known as group 7A. Group 17 elements are also referred to as halogens. Now group 17 elements have 7 valence electrons in their outermost valence shell. Group 17 elements, they gain an electron in a reaction and become negative ion with -1 charge, giving them an oxidation state of -1 or oxidation number of -1. So the 6 elements of halogen group are fluorine, chlorine, bromine, iodine, astatine, and tensine. So tensine is a reactive material. So group 7 elements have 7 valence electrons with an oxidation state of -1. So halogens, they need only 1 electron to form a full octet. So that is why they gain only 1 electron in the redox reaction. Now the term halogen, so why did this group, or how did this group 17 get the other name as halogens? Because the term halogen refers to salt forming elements. It is derived from 2 Greek words to make salt. And that is how the name halogen came into existence, labeling the group 17 elements. So halogens like chlorine combine with metals like sodium to form a common table salt, that is sodium chloride. Now let's examine the electron structure of both sodium and chlorine. To understand the concept of why sodium in group 1 loses 1 electron, while chlorine, being a group 17 element, gains 1 electron. So when you examine the electron structure of sodium, it has 1 valence electron. It loses its only valence electron from the outermost shell in redox reaction, that is when it reacts with chlorine, to form a electropositive ion with +1 charge. So what is the driving force? The driving force for the sodium to lose the outermost valence electron is to attain the stable electronic configuration to that of noble gas that is nearest to it in the periodic table. So neon is the only noble gas nearest to it in the periodic table. That is why it was only 1 valence electron. So sodium has to lose 1 electron to attain the stable electronic configuration of neon, because as I already mentioned, noble gas nearest to them in the periodic table. So sodium undergoes oxidation and is oxidized in the reaction. So what about the chlorine atom? So when you examine the electron structure of chlorine, you'll find that there are 7 valence electrons. So chlorine, it gains 1 electron given by sodium to form a negative ion with a -1 charge, giving them an oxidation state of -1. And what is the driving force for the formation of chloride ion? Because to attain the stable electron configuration of argon. So argon is the noble gas nearest to chlorine in the periodic table. So chlorine has to gain 1 electron to attain the stable electronic configuration of argon. Reason, noble gas nearest to them in the periodic table. So chlorine undergoes reduction and is reduced in the reaction. So now you know the reason why group 1 elements lose 1 electron from their outermost valence shell in a reaction, while group 17 or group 7A elements gain 1 electron in a reaction. So to attain the stable electronic configuration of the nearest noble gas in the periodic table. Coming to the interesting group or the last group in the periodic table, that is group 18, is also known as group 7, group 8A or group 0 elements. So group 18 elements are also referred to as noble gases. Group 18 elements have a total of 8 valence electrons in their outermost valence shell. Now, an outstanding feature of group 18 element is that they have a stable electronic configuration with a total of 8 valence electrons in their outermost shell, and therefore they do not gain any electron, nor they do lose any electron, nor they do share any electron, and that is why they do not participate in any reactions, and as a result there is no charge associated with the group 18 elements, giving them an oxidation number of 0. And that is why, because of their oxidation number, it is also called as 0 group elements. And that is why they are also referred to as noble gases, because of their noble or ideal behavior. So group 18 elements, the name of noble gases: helium, neon, argon, krypton, xenon, radon and oganesson. So group 8 elements have 8 valence electrons with an oxidation state of 0. They are also called as noble gases. The noble gas oxidation numbers in their elemental form are 0 due to their unreactive nature, and as a result there is no charge associated with them. And that is the result, they are chemically inert or unreactive. They neither lose electron, nor they gain electron, nor they share electrons. Please don't forget to subscribe my channel, share and like my videos. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.